Hello everyone, this is Lama Nayal. I will present my failure mode effect analysis project in Metro Mall design, which I did with Vidya Bassani. What is a failure mode? The failure mode is anything that might go wrong in a product or an input or any process, and in a result of that, this process or product will not be doing its intended function. The Fmea began to be used at 1916 in industry, and after that it was developed to be a very effective tool in increasing the quality and prevent defects. Fmea is a structured approach that helps us in identify the ways in which a product or process may fail and estimate the risk associated with these specific causes and prioritize the actions that should be taken to reduce the risk, and it helps us also in evaluating a design evaluation or our current control plan. This is the Fmea form that shows the process step or input, its potential failure mode, its potential failure effects, and its severity. What does it? What means that how important this failure mode will be, how important the defect it will be, what kind of damage it will happen, and then its potential causes, its potential what is the occurrence of this defect, what is the current controls for this defect failure mode, for this failure mode, and the detection of this failure mode. So in result, we will be able to find the priority number of risk for these things, and then we can give the actions recommended. To do a failure mode effect analysis, we must begin with determine the ways in which the input or the process can go wrong. Then we must determine its effect. So in this case, how much the severity of this failure mode. If it is too serious, it will get like number 10, and if it is not that serious, it will be 1. Then we will identify the potential cause of this failure mode, and then what is the current control for this. The potential causes, it will give the occurrence, and the current controls, it will give the detection. By multiplying the number of severity and occurrence and detection, we will have the risk priority number, so we can see which problems are so important, which is more than 100, and we can work on it. And if it is less than 100, we can skip it. And even everything more than 100, we will know which one are most important, so we can begin with that. Now in MMD, that produce fuel cell, which is a kind of device that converts chemical energy into electricity through a chemical reaction. There is 3 kind of products in there, which is monolith, supercooler, half supercooler, that goes into 3 sections, which is preform, lamination, manufacturing. Our product scope was in lamination, that has 4 stages, which is laminating the products, heating them, cooling them, and then deassembling them. So in loading lamination, we were able to find many failure modes, which are included in or summarized in missing captain sheet. And this is the captain sheet. This captain sheet separates the products between each other. So when it is missed, the products will not be able to remove from each other, and the detection of that is 100. That is a very low importance number of priority risk. Sometimes a cracking preform can happen during the loading, which is kind of mishandling. Also, its priority number is 8, but these both failures have a very big severity, which is 7 and 8. But because the detection is so high, also it gets a low priority number. Sometimes cutting the FEP film happens not in a correct way, which can cause kind of difficulty in delamination. The severity of a problem of this was 147 because its detection is not that high. So we recommended to update always the correct dimension and have like a standard sample to show the correct dimension. Sometimes workers do improper order while doing the three kinds of a product. That will give a non-acceptable finished product, which is with the severity of this failure mode is too high, which is 8. And the total priority number of that is 20. So we recommended to have like a sheet that each worker can check the right way that he is building the molding. So whenever he puts a kind of materials, he will check it, and in this case we can reduce the defect. There is a failure mode in transfer cycle that which might be too long or sometimes too short, and that cause some internal resistance issues. And this priority number of these failures was so low, which is 1072, so we can skip it. For lamination cold press, sometimes the parts can press be too long or not enough long, or sometimes the pressure is not enough. So that causes some IR also issues, and it may increase the cycle time of the process. But also the priority number of these problems is so low, so it was 72, so we can also skip that. For post-lamination, sometimes the workers release the capital in not a proper way that increase the IR. The severity of that is 8, and it has a high priority number, which is 120. So we always need to check how our data to know which workers are doing that, and to train them more on that. Sometimes ding and dents can happen. The severity of that is too high. That's because of mishandling. Also, the priority number of that is 120. More training will be benefit, and we must always review our data to know what's going on in each shift. Sometimes we have cracked parts that may cause a teeth migration, which is too important, but the detection is, of that is kind of high, so its priority number is 72, which we can keep that. Sometimes dents happens also, that dents happens like while in the molding for supercoolers, that will damage the tube, and the severity of that is too high. And the occurrence of that is so high. Also, the detection of that is so high. So it gives a very high priority number, which is 329. So we suggest to redesign the supercooler modes to prevent these failure modes. As we see that we were able to identify 19 failures in the lamination process, and we calculate their number of priority risk. And 7 of them was really important, so we give some recommendation for that to improve the process. Thank you.